Let's play a game. We're going to create a triangle and select a point within it. We then pick a random corner from the triangle with half the distance toward it and repeat. After a few thousand repetitions, we see something amazing. This is the Sierpinski triangle, a fractal. Fractals, in simple terms, are infinitely complex shapes that are self-similar. They are made up of an infinitely repeating pattern, where smaller parts of the pattern look like the entire thing. The Sierpinski triangle is a perfectly self-similar fractal, since parts match up exactly. But when defining fractals as self-similar, we run into a problem. All kinds of shapes, not just 2D ones, can be seen as self-similar. Splitting a line into two creates two lines, where each is half the original length. A square can be split into 4 copies, where each is half the length. And a cube can be split into 8 cubes half as big. In each case, we see self-similarity. The place where fractals differ is in the dimensionality. If we try talking about fractals through regular dimensions, it doesn't really work. With the Sierpinski triangle, for example, creating it out of a line leads to infinite segments and therefore an infinite length, which doesn't help us when talking about the shape. Additionally, trying to talk about it as a 2D shape with sections removed leads to an area of 0, since an infinite number of sections have been removed. We cannot talk about fractals through normal dimensions, which is why we use fractal dimensions instead. We see a pattern if we look at our self-similar shapes from earlier. When you scale a one-dimensional shape by a half, the original is twice as big as the scaled one. In the same sense, a two-dimensional shape scaled by half is 4 times as big as the scaled one, and a 3-dimensional shape is 8 times as big as the scaled one. We can see that the ratio between the shape scaled by half and the original is always 2 to the power of the dimension. This is in fact true for any scale of x. We can use this to effectively define dimensions. Scaling the Sierpinski triangle by a half makes it 3 times smaller than the original. This means that we need to find the answer to this equation. And we can do that easily with a logarithm. This helps us find 2 to the power of what gives us 3. We find that the Sierpinski triangle is indeed 1.585 dimensional, and that's precisely what defines a fractal. They're infinitely complex, they are self-similar, and they have a fractal dimension. The perfect geometrical fractals we have seen so far are but a fraction of what's out there. Benoit B. Mandelbrot, who coined the term fractal and discovered the Mandelbrot set, conceptualized them in a broader sense, looking at them as a way of modeling the intricate roughness of nature, converse to the needlessly smooth nature of calculus. Along the same branch as the irregular fractal structure of broccoli or the replicating structure of a fern. Naturally, chaotic fractals reflect the randomness of nature. The Mandelbrot set, made with a simple equation, presents to us an unending beauty. There will always be more to explore in the infinite depth of fractals.